We're going live. We're going live. We're getting ready. We're getting a little bit ready as well. Okay. Getting started with the lives. Good evening, good morning, and thank you for joining us. Here's the book for today as well. Well, one of the books. There will be more. I'm just gonna feed them their dinner, and we'll start with our physics class of tonight. Please do like, share, and subscribe. Thank you guys. Thank you for joining. We're getting started. Hi, Fuji baby. Come. Let's get back. Well, get back from the gym. Then set up. Yes. Indeed. Start our physics, astronomy, astrophysics, and cosmology live. Thank you guys for joining. Please like the live. Can we get 10 likes? Can we get 10 likes? Can we get 20 likes? You go. Come, Baji. I'm going to read your comment in just a second. Thank you for joining. Thank you for joining. Can we get 10 likes? Thank you so much, everybody. We're just doing kitty feeding time, and then we'll get started with my face on the live and physics. See them eating as well. Hey guys. Hello. Hi. Hello everybody. Thank you for joining. Could you please like the live? Thank you guys. Okay. We are here. Hi, Fuji baby. Okay, just shut up. Okay, no. All right. Well, tonight we actually have a few different plans of topics I want to share with you guys. Put a little jacket on here before I sit down. Thank you for liking the live. I have a few different topics that I have in mind. Here you go, Fuji. And we're gonna get started here with that. Huh. Do appreciate your patience. The usual stuff is going on here. It's okay, Fuji. You finish without a rush. It's okay, Fuji. Hi, guys. How are you guys doing? Hello, AW. Astrophysics for People in a Hurry is one of your favorite reads. Oh my gosh. We do Lion's Aunt. Yes, this is us. We do use the book quite a bit. Hi, Reese. Hi, Amanda Garsha. Hello, Amanda. Hi, Justin. I made it Dad's birthday buddy. Oh, wow. Happy birthday to your dad. If that's what you're talking about. Are all the buttons buttoning? I've been sick, guys. So I've missed you. Hi, Dominic. Hi, Caleb. Hi, Produced. I had the flu. I did. Okay, I'm gonna move this down so Baji, you can have it. I have had the flu, so I missed some of the, well, I missed coming to my own live. Well, while I was recovering. Let me get my, what do you call, needle container, because that's kind of my appropriate, um, what should I call? So I have a few things that I did want to cover. Um, but then I also have another whole topic that I wanted to go over. So we'll see. We might cover something from this one, but hi, Dominic. Just trying to get you to remember who I was. I do remember your username just in case. So, by the way, this needle container, which is milk powder, is the one that this phone will rest on. So, here we go. Here I am, guys. Here I am wearing a blue dress. See, this is my blue dress. And so I've matched it with these blue earrings. I hope you appreciate. I have been recovering from a terrible bout of flu, and today I also went to the gym, and I'm back from the gym, and I am here with you, and we're gonna get started with our physics live. I want to donate $500. Hello, Dominic. Can you like the live? That is totally free, and you can also subscribe, which is also free. Now, if you want to become a member, that costs a very small amount of money. But you could also become a member to help support me. I think it's a few dollars per month. Um, do I have kids? They are feline, but yes. You share a birthday with my dad. Oh, thank you. MGA 84. Hello. Hello, Kaden. Are you pregnant? Not that I know of. In the US, that is supposed to be not a question that you really ask a woman. Do you have real kids? These kids are pretty real. They're not artificial intelligence. Um, but if you mean human babies, I am simply a cool auntie of some human babies, not my own uh, biologically produced children, but they feel like they are my own. Hello, Elijah. No canines in the home just now, but felines, yes. But I am a fan of canines as well. And I didn't know that I was such a fan of human babies either. But recently I met one, and I have to say, I may have met my favorite human baby, guys. And I don't know if I'm just biased because he is 50% same genetics as me, unless I'm adopted, which could always be something, you know? Uh, so, this phenomenon where when you're an auntie, you feel like the kid is kind of like yours, but they're being raised by those other people, your siblings and whatnot. This phenomenon is something that I am getting to experience at the moment. So if you're an aunt or uncle, let me know. Hello, hi me. Do I want a baby, baby? Damn, mama, you a smoke show. Hello, Mo guy. Hello, Rengo. Uh, okay. Hello, the David Juliet. You look like an Indian. Brian is saying, I love you. Thank you. Hunter is saying, hello. Karen, don't ask that question. Hello, KJ. Hello. Who is here? Oh, Reese is here. I was gonna say who's timing these people out. Is it Ben? Ben, are you here? I do want to know if Ben is here, given all of the things that are going on in this world. But I see that Reese is here. Now, Reese, you've been gone quite a bit. What happened? How are you doing, Reese? Spilled some of the tea of your life as well. I told you I had the flu, so I was gone. Sorry about that. But Reese also has a baby. So there's people with babies all over. So how are you and the baby, my mod? So let's see. Will you be my girlfriend? Says Ken Ruby. Are you a girl that's asking that? Alex Ran is saying Cosmos. Hello. Yes, we will definitely talk about that. You are cute. Oh, thank you. Hello, Andrea. Hello, Vishal, who's gonna welcome me. Hello, Vishal Tyagi. How are you doing? Are you Asian? I'm glad you said Asian and not are you an Asian? Doesn't sound the same. Ella, Vala, Ella, sorry, Ella. Keep it up, girl. Thank you, Ella. Christy is saying hi. Hello, Christy. Hello, Allenbert. I think this is making it harder for me to read. If I read it on the background of my jacket, then it will be a little easier for me. Thank you, Ella. Do you cook butter chicken? No, but I do order it. Well, actually, I don't order it. My friends order it, and I tolerate this mundane order of theirs. Hello, Sean G. Are you ticklish? I am. Doctor is saying, eat it up. Okay. Just been busy working and looking after Charlie. He's fine. Thank you for asking. Oh. Alum Burt. Hello, Alum. I have some Irish DNA. I like your stream. Thank you, guys. Can you please like the live? These are some weird questions. Thank you, Justin. These are pretty tame on this channel, actually. At this time, unfortunately, I do get being a night owl has its pros and cons. This is the time when it gets very crazy here on these lives. Hmm. I can give you a JC Penney gift card. Um, okay, do it. Send it over. I like your dark circles. Oh, okay. Thank you so much. My name is Olivia. Yourself, so beautiful. Hello, Olivia. I think they like you. Hello. Hello, 78 Yusuf. Are you an astrophysicist? Yes, actually, we are going to talk about astrophysics right here, right now. How was my week? Well, it's just getting started. I actually did go to Boston and I took a bunch of videos and pictures for my TikTok because I also do TikTok. Boston Girl is the handle on that one, but this channel is dedicated to physics, astronomy, astrophysics, cosmology, and kitty cats. So you're in the right spot for that. Hello, Marcia or Maria. Mm, Brene, how are you doing? My crush girl rejected my proposal on 13th February. I still can't forget her. It makes me feel sad and depressed. Uh, 13th of February of this year, you mean? Seems like a long time ago. Perhaps you should move on. Do I have lotion here? What is this? I brought this little bag down because I wasn't quite ready. I wasn't quite. Uh, oh, this is a foam cleanser. This is a bag that I sometimes take. Look at this little nice little mirror I have, by the way. I got this. I got this as a gift. Um, I think from a brand, probably, but that was a long time ago. So, anyway, this is my little bag that I carry sometimes, and hoping, I was hoping it has more lotion than it currently does. But, anyways, I kind of came down with it because I wanted to get the live started. So, thank you guys once again for being here. I think what we will do, people on the internet say the darnedest things. They do. Thank you though for being here, everybody. And please do like the live and please do share the live. Hello, Randy. We miss you so much. Oh, I'm here. It's not easy to move on. Okay. Sorry about that. I'm sorry she said no. Um, it happens. It happens, Brunei. It happens. The more you live, the more people say no. And what you could do is say yes to yourself and take yourself out for a nice Valentine's Day dinner. Okay. What's your take on dinosaurs? Where to buy plutonium? I just have my ID and one bank card. Why can't you use the moon's gravity to power my cell phone? You had nose surgery. I'm on theoretical physicist. When will you get married? I subscribe. Thank you for subscribing. You have not been on. I was sick. I'm sorry. My throat was very bad. It's actually still a little bad, but it's good enough. I had the flu. I had a horrible sore throat. I was very sad because I couldn't do the gym, and that's like very much necessary for my mental health. But today I even went to the gym, so I'm recovering hopefully. She looks somewhat like you. Do you have a boyfriend? Hello and God bless. Hello, Lombi. Hello, you rock my world. Oh, so pretty. Okay. She is not single anymore. Who is not single anymore? So, Pranay, please let the others know about your entire love story. I don't know if I'll keep up with it. Um, and I will get started with all my things. Okay. So, hello, B Dog. I'm here. You remind me of Walter White's ex-girlfriend. I don't know who Walter is, White is, or the ex-girlfriend. Your voice sounds good. Thank you. This voice, this $1 million voice was very bad. My throat was hurting a lot last week. I had the flu after my travels. A strain of flu that I clearly don't have the shot for because I also got my flu shot last year in the fall, and yet I got the flu. So there's that. Okay, well, hopefully I look presentable. Um, Sorry, their food is falling from the auto feeder. Mm. I get ill quite a lot. What do you mean? Hi, Frances. I have 4 paper on unification I'm trying to publish. Thank you, 78 Yusuf. You should maybe share some of the things in the chat here. You got insulted by who? Can you sponsor me on archive? I need help. I'm not sure how that works. Can people sponsor people on archive? But certainly you should share your findings and your theories here in the chat so people can learn what you worked on, okay? So now let me share the live. Ben, did you get the COVID vaccine? Yes, I did. I get the COVID vaccine like, am I saying it? I get the COVID vaccine every year. Are you saying that's why I'm getting sick? I got COVID, I got the COVID vaccine, everything. I've had COVID as well a couple of times. Like I was sick. That's how space-time bends. Can you sponsor me? If you don't mind me asking, are you Christian? Hello, Elissa. Do you speak Punjabi? I can understand Punjabi quite well. But I mean, I speak Hindi. Definitely did not get a COVID shot. What was your thesis on? Actually, we've been covering from my thesis. So partly I wanted to see if you guys wanted to continue the discussion from last time on my thesis. It is on particle astrophysics, and we did cover some part of it, the beginning part, sort of the introduction of it here in the live in the past. So we might continue that either tonight or next time. Um, but yeah, those are the plans. And then also I have a topic picked out from the Neil deGrasse book as well. Hello, B Dog. I'm currently at the gym hitting 130 pounds. Hello, Anthony. Let's go. That's why I'm here. Hello, Justin. Oh, do you want to maybe we'll do my thesis first. Okay. All right. Let me do my thesis. So tonight, I think what we'll do is we'll talk about Cherenkov radiation. So last time we had remember we had been talking about uh particle astrophysics and an introduction to it, and we even saw some of the messengers of astronomy other than visible light, such as gamma rays, as another type of light, neutrinos, cosmic rays, gravitational waves, and what else? Was there anything else? Remind me. So we talked about all those types of things, like what particle astrophysics in the modern day and age kind of means. Um, One second, please. Let me share the live, sorry. Okay, I thank you for the hearts and likes and stuff. Really appreciate it. Thank you, Ben. How are you? And where are you? Are you here yet? Are you in New York, Ben? Okay, and then I'm gonna say like and subscribe. Thank you, guys. Well, I did not have a, what do you call? Um, it's not a bacterial infection. Had a viral infection, so put my hair down. It was in this clip that is a little painful on my neck. Okay. Sorry, guys. Let me set it up on the laptop as well. But I'm glad to see that you guys are chatting amongst each other. So tonight, I think we will keep on going with Cherenkov radiation, which is basically the part that we were on last time. And I'm going to show you once again about the messengers of astronomy so that we get a little bit of a recap. Show you my outfit? Okay, I can do that. It's a blue dress with a black jacket on and these blue earrings and rings. I'm a ring girl. But I can get up to show my outfit, I suppose, even though I'm quite comfortable. 1 second, please. Please do. Keep on keeping on. Thank you guys for subscribing. Are you from Texas? Hello, brawler. Hello, Crystal. You're so potty pretty. Thank you. Thank you, guys. Really appreciate all of you being here. Okay, let me show you my outfit and then I gotta sit down. Don't ask me again. So, this is the dress. It's very full length. See, I'm going far away so you can see it's very comfy. It's actually a dress from Amazon. I am an Amazon influencer, but I got this dress a while ago before I became an Amazon influencer. So, it's a very comfortable cotton full length dress. As in, you don't have to worry about the dress not being long enough. Like I can be really comfortable in it. I can sit however I want. I used to wear this to work a lot. I have this dress, the same dress in multiple colors. Like I have this in blue. See, this is blue. It's fully blue. Like there's no other colors. It's all blue, all blue. And then I put this little black jacket on. But I have this dress in this color, blue, red, and black. I really like the black one because I somehow think that it's even more just like wearable. Like you can just dress it up more with like accessories, or you can just wear it as a simple dress. So these dresses, again, I don't have the link for them right now. Maybe I can find it on Amazon actually. Now that I'm an influencer, I might be able to like search for it and give you the affiliate link, and if you want to buy it, go ahead. It will help me. But this dress is years and literally I used to wear this dress in grad school. So it's years and years and years old, and I wear it regularly, and I put it in the wash and the dryer and everything, and I've had it forever. Like this dress is now 8 to 9 years old. No, maybe even 10 years old. So, like I've worn it a lot in grad school, so it has survived grad school. It has survived working in corporate America, and it has now survived partway through this live. So, that's the dress. Okay. I'm so sorry, but now I have to find the dress and give you the link because Amazon is actually a little mad at me for not having enough sales because I'm a terrible influencer of Amazon, apparently. I don't tell you guys enough about all the things you could buy there, which I don't know if I really, want people to buy things nonstop on Amazon, so I probably don't do it. Um, but this dress I can testify. Oh, there it is. Oh my God. I found it. Oh my God. I can't believe this dress. This dress is called the women's short sleeve crew neck. Is this a crew neck? I guess it's a crew neck. I don't really like see for work and grad school and stuff. Hi, car HGK. For grad school and work and stuff, I don't really like dresses that I would have to be like uncomfortable in because I want to like throw on the dress and be ready for work and school for like a whole day. So I like the neck like this and I like the full length. In fact, um, one of my colleagues once asked me if like my culture doesn't allow me to like wear shorter dresses because I always wear these longer dresses, but I just find them very comfortable. Like this dress is just really comfortable and it looks good enough for work and that's all I really care about. So, women's short sleeve crew neck, long maxi casual loose dress, medium size royal blue. And since I am a little bit royal, uh I have this dress, and here is the link. Girls, women, and children, and gentlemen, go ahead. Go ahead with that dress. You can get it if you want. It's on Amazon. Hopefully, it's in stock. You can get it. Royal blue dress. Ben, you have the link too if you want to get it for your wife. It is full length, and I am 5 feet 4 inches. 5 feet 4.5 inches, and it goes till my ankles. I hope that was a good dress demo for you guys. Ladies and laddas, ladies and gents. Oh, and my socks are from Bombas. Whatever that means. Bombas. These are Bombas socks right here. See how this dress, like, look at this. This is such a flexible dress. Like, the dress literally covers everything at all times. Hello, to-do. So I have Bomba socks on, royal blue dress on from Amazon, which magically fits everybody. And it's extremely, oh no. And it's extremely comfortable, and I've been wearing it to work for literally 10 years. So, since somebody asked, feel free to buy it. Buy it and wear it. It is all genders can wear it. I'm gonna say that. Sometimes my guy friends want my dresses as well. So there is that. Feel free to buy it and wear it. There you go. So now tonight we're going to talk about Cherenkov radiation from my thesis. So let me change the title. Cherenkov radiation. By the way, We're going to talk about the speed of light in a medium that is not the vacuum medium. It's going to be a dielectric medium. It is going to be ice, actually, specifically the Antarctic ice, which is why the experiment is set up in Antarctica, or was for my thesis. And just keep in mind, before we get into the details of Cherenkov radiation tonight, that we're going to be talking about light traveling through a medium, or the speed of light in a medium that is not vacuum, but ice, which is a dielectric medium. Oh, and these earrings are from a random gift shop in West Virginia, like as in a nice gift shop on a hill in like a individual gift shop. El Challen, how are you? So these are from West Virginia. The dress is from Amazon, I told you, and I forget where I got the black thing from, the jacket. Probably also Amazon. When I was in grad school, I used to buy things from Amazon a lot, and that was years and years ago, so this dress is like 10 years old now. Feel free to buy it and wear it. Cherenkov radiation, live study with me. Oh no, these are not right. Okay, let me fix the. Okay, this is going to be in the realm of particle physics and particle astrophysics. And astronomy, of course, is what we will be studying tonight. Okay, Cherenkov radiation, live study with me, particle physics, astronomy and astrophysics, the royal blue dress I shared. I'm gonna put a playlist for this. I'm gonna say done, save. Mr. Drew, are you being extremely naughty again? You need soda ice? Hello, Louis. So I showed you guys my dress. I almost never do that. I didn't think of it as anything of consequence. Um, but you know, I have to remember that people do like to see that stuff sometimes. And on top of that, I am an Amazon influencer. I am. I try to tell my Bengali, hello, I am a Bengali. That's funny. Thank you for being here. Please subscribe. You better not be. Hi, Delaware. What do you mean, better not be what? Better not be what? What you mean? Okay, and I gave you the link, right? That's the link for the dress. Drew is naughty. It's true. There are some people who are quite naughty. Okay, guys. Well, thank you so very much for being here. Indeed, I made a goal. I shared the live. I have the link for the dress. I have done all the housekeeping that I can think of for this live. And I thank you so very much from the bottom of my heart for being here for physics class tonight. And I had the flu, so I'm so sorry. I missed you guys so very much last week. We have the link. Okay, good. Ben, you should get it. Let me know if the link doesn't work. Okay. I know Ben shops for his wife a lot. Ben is a good guy. There are some people here who have wives who are not shopping enough for their wives, but Ben shops for his wife. All right. Now let me show you as a reminder. Let me turn this and show you as a reminder. Remember, guys, we talked about multi-messenger astronomy last time. We talked about how generally we look at the night sky, and we did astronomy traditionally with optical light. So for the longest time, for years and years, for hundreds of years, astronomy is one of the oldest sciences. It might even be the oldest science. We used to do astronomy just by looking at the night sky, seeing the optical light, which can, of course, enter our eyes and get processed by our eyes and our brain. And because of the shape and the size of our eyes, that is the light that we can process and see with. So optical light used to be our way of doing astronomy in the long, for ages and ages. And of course, we also started to use it with telescopes. We of course see we know of Galileo Galilei as the father of modern astronomy, who of course gave us a bunch of discoveries with his observations and telescope. And that was all pretty much using this optical light. Now, as you know, Galileo himself is quite old, hundreds of years old at this point. So, literally, for the longest time, we've been doing astronomy with um, optical light, the visible light that we can see with our eyes, with human eyes. Okay. So, now, really, actually, there's many wavelengths of light. Also, the same thing as saying that there are other frequencies of light that we cannot see with our eyes, but that do exist. And pretty much the longer the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency. So now that we do multi-messenger astronomy, we have something called gamma rays, for example, right here. And these are going to be really short wavelength or high frequency types of light. So now light is a dual wave and particle nature thing. And so gamma rays, having the very short wavelength and high frequency, is almost like a particle nature more than it is a wave. Okay. So when you go into those really high frequencies, it's almost like you're getting hit by individual particles, which is, of course, consistent with the fact that light has a particle nature. And pretty much with something like gamma rays as being the type of light that we may use for detection of various phenomena in astronomy and astrophysics. If you're doing it with if you're doing with light that is gamma rays, you will need a detection method that, of course, is sensitive to gamma rays. Now, traditional telescopes, the one that we saw on the left over there, is not going to be the type that can see gamma rays. You're going to have a very different kind of instrument, some other way of measuring the gamma rays. And you might have heard of something called a Geiger counter. If Ben, can you put something in the chat about what a Geiger counter is? That would be really helpful. But basically, it's something that can literally, it's counting the photons that it is getting hit with. Because as I was mentioning, and this should all kind of be consistent with that frequency and wavelength thing that I was saying, um, really at the gamma rays, you have light as more of a particle nature. So literally, you're counting the number of photons that is hitting your instrument, and you're getting your gamma ray measurement. So you need a telescope, right? An instrument like that in order to get gamma rays, and to use gamma rays as your yes, oh perfect, yeah, somebody's putting something in the chat there. Cosmic, thank you. So you need something like that. Your telescope and your detection method needs to be different in order to be sensitive to gamma rays. And let's say some event or some object in the sky is emitting gamma rays. For example, we do know of transient events like gamma ray bursts, which can be either from hypernovae, which are really big supernovae, or they could be from, neutron star, or black hole, or neutron star black hole mergers. So short gamma ray bursts or long gamma ray bursts, in other words, of course, emit gamma rays as their signature emission. So those things can, those events could potentially emit other things too, but the one thing that we know for sure they emit is the gamma rays, and hence they're called gamma ray bursts. So if you are wanting to measure the signature of such events, then you of course you'd need a gamma ray burst, or a gamma ray detector. Okay, so just keep in mind, I'm saying a little bit about each of these because um just keep in mind, like, you want to be thinking about what is the signature that you are looking for, that you're doing your astronomy with. Is it going to be visible light? Is it going to be gamma rays? Is it going to be cosmic rays? Is it going to be neutrinos? Is it going to be gravitational waves? And depending on what it is, your setup will be different, your experiment will be different, the measuring device will be different, and whatnot. Okay, and what things it does also, it's going to be different. So here's the next messenger we have is cosmic rays. We talked about this. These are charged particles that, something can be, it can be as simple as a proton. Really, a proton has charge. There's a lot of protons in the universe because the most abundant element in the universe is hydrogen, and hydrogen, the simplest form, is just a proton in the nucleus of the hydrogen. So we've got potentially a bunch of these, and depending on their energies, they can do different types of interactions and whatnot, and you might be looking for the interaction of that, or sorry, the signature of that interaction, depending on if you're looking for cosmic rays. So sometimes these cosmic rays can, come in and produce air showers, and really, like, the energy of those and things like that would be all under scrutiny if we think that it's, caused by a cosmic ray of interest and whatnot. So that's the cosmic rays. Then we've got neutrinos. This is a type of particle. We introduced this, of course, last time. It's a lepton. It's in the same family of particles as the electron, but it is a lighter, much lighter, and no charge cousin, I would say, of the electron. So it is not the electron, it is not like the electron really, but it is in the same family as electrons. And but it is, quite different as well. And then lastly, we have gravitational waves. I'll just, wanted to show you all these, what do you call, all these different types of multi-messenger astronomy. Um, you're not seeing any cats. Well, here is a little, let me see. Here is a kitty cat. There is always kitty cats around, with the thanks to the universe and evil eye remove. Um, so basically, hi, hello to Boston. So gamma rays, UV rays, yeah, so gamma rays are going to have more energy as well, because the energy of the photon actually goes, is proportional to the frequency of the light. So it's actually Planck's constant times frequency, and so the gamma rays are more energetic than, say, visible light photons. So UV rays is another type of light. So they're all related in the sense that the different this is all light, but different wavelengths and different frequencies of light. So, uh, more energetic form of light is going to be the gamma rays. A bit less energetic is going to be the UV rays. Okay, so it kind of depends on your processes. Like, if you have a really high energy process, or site, basically, then it might be making gamma rays, and then we get those gamma rays out of that thing. But if it's, for example, like the sun, the sun actually makes UV rays, because the sun is not the site of the most energetic um, processes in this universe. I mean, thank goodness, right? A sun is, uh, at the end of the day, a pretty tame star, which is still young and still doing its thing, just going from hydrogen to helium. It's a nuclear reactor in its belly that is making helium out of hydrogen. So, um, you know, it's not the most powerful particle accelerator or anything like that, thank goodness. Which is why it continues to be the sun, and not something else. So if you have a very high energy, a much higher energy type of astronomical site, where particles are getting accelerated like crazy, then you might expect uh, something like gamma rays. But the sun, for example, will make UV rays, right? And that's why we put on the sunscreen lotion, um to protect against that, because even that can be harsh on our skin. So you know, the more energetic the light, the smaller the wavelength, and the higher the frequency, and it can kind of penetrate our um, skin and body and stuff like that easier, and cause some damage. So gamma rays would be really bad to be exposed to. They're much they're basically the highest energy photons. Okay, so we wouldn't really want them going into our eyes, anyways. Um, you know, so um, hello everybody. Hi, Music Gen X. Um, I see the question. At first, I read it a bit differently. Let me think about that one. Did life start here, or did it come here? Um, Hello, cat. Your voice is like AI. Well, it's definitely not. It's a real human voice. One is from sun and one is from nuclear. Um, yes, Planck's constant times frequency, but where the Planck name actually has a C in it. Planck is Planck. Okay, this is a guy, Planck. And if you look up Planck's constant on Google or wherever, um, you will see what it is. There's a value of it, and that times frequency is the energy of a light photon, of a photon. So um, when you have a higher frequency, like a gamma ray, then that light is more energetic. Somebody did a super chat. Oh, thank you so much. Steven Sky Reading has done a super chat. Thank you so much. Steven, thank you. I'm contagious. Well, I've been sick for over a week. I hope I'm not contagious. Any connection? Okay. I think I got some of your questions. Thank you for That's right. Uh, your Hulk, I believe, got exposed to gamma rays in the fictional story there. Thank you, Lysergic. Okay, so we'll keep going. I wanted to show you the multi-messenger astronomy little introduction picture there, showing you all the different types of messengers of astronomy that we use now. making the point, of course, that we used to use only optical or visible light, but now we can use gamma rays, we can use cosmic rays, we can use neutrinos, and we can use gravitational waves. Um, of course, the discovery of gravitational waves within the last decade has been a huge step forward in this realm of things because you know it's another prediction come true from general theory of relativity, as well as it's really cool to pick up on gravitational waves from these far away um, events like neutron star colliding, or black hole colliding, something that was of course connected with short gamma ray bursts, but we then got evidence directly that that is the case. Okay, so we've come a long way from hundreds of years ago when we used to only do the traditional astronomy with traditional visible light. So now we will go on to the topic of neutrinos as a um, multi-messenger astronomy uh, messenger option. So neutrinos is the focus of my thesis here that I am going over here. So neutrinos are, first of all, they're a particle. They are a fundamental particle of nature, included in the standard model of particle physics, which is of course not necessarily a complete model, but neutrinos are part of it. Now, for the longest time, people were a bit confused about whether neutrinos even have a mass or not, because that's how low mass they are, a very tiny mass. Um, and it seemed like there were like three kinds of them, three flavors of them. So people almost thought that these might be massless particles, is how low mass they are. And also they do nothing almost. They do very few, very little interacting, basically. So when I say nothing, in particle physics, they interact weakly or through the weak nuclear force, and you know that is that most things do more than that. So for example, electrons have a charge. They can interact with electromagnetism. So they have a negative charge, so they will experience electromagnetic force with, for example, a proton which has a positive charge. And electromagnetic force is attractive for opposite charges and repulsive for like charges. Those types of things don't exist at all for the neutrinos. Neutrinos don't have a charge. So there is no such thing as the charges and being repelled or attracted through charges. Okay. So the only real interaction for neutrinos, well, one is gravitational. We know it has a mass, so it will have some gravitational interactions. But then the only one out of the fundamental non-gravitational forces that it seems to interact through is the weak nuclear force. So this particle has been elusive because of its lack of interaction in other methods. And not having a charge also means that you can't really see it getting bent around by any magnetic fields or anything like it. That doesn't interact with other charged particles in that sense through the charge. And charged particles like cosmic rays can get bent uh, with a magnetic field. Like the galaxy has a magnetic field, or Earth has a magnetic field. Uh, these are pretty common to have. So when you have a charge, and you're coming from a large cosmic distance away, you could get bent around, and your original source can be basically hard to know if you interacted with the magnetic field along the way. And you don't really point back to your original source anymore. But in the case of neutrinos, because of their lack of such interaction, they do actually point back to their original source if you can catch one here on Earth. But of course, the same thing that makes them a very potentially reliable messenger of astronomy is also what makes them very difficult as a messenger of astronomy, in the sense that they're elusive. So you're going to have a very smart, clever way of detecting the neutrinos
and letting them do some kind of interaction. We know that they don't interact much, but we have to let it do something, and then we have to kind of catch the signature of that interaction through some methods and have a whole detection method story with that in mind. So it's not trivial, and so we're going to get into that now. So basically, neutrinos, depending on your energy. So we also talked about last time. I'm not going to go over it again right now because I want to get into this. But last live we talked about the energy regimes um, that we can think of with all this work. So the energy regime that you're working in is very important. Depending on the energy of the neutrino, you will have a different kind of device or measurement method, detection method. So keep that in mind. But basically, in Antarctica, the place of my PhD thesis, that place and its ice is used for a number of these higher energy types of neutrino experiments, and we use the Antarctic ice as a detection method. Mm. Okay. Now, basically, something to keep in mind is if something uh, interacts very little, um, then, and you still want to find it somehow, then you either have to wait a really long time and hope and pray that it interacts, or you can give it a lot of detection medium, or what we call sometimes instrumented volume, for it to basically interact, and then you instrument the the material uh, of that medium, and hopefully you see some kind of interaction. So that is where Antarctica comes into play a lot, because Antarctica is mostly ice, and this ice is what we are using as the detection medium for our neutrino interactions, and picking up on these interactions somehow through through we hope we expect, we predict that it will have certain amount of interactions, and we try to um, get the signature of that interaction and measure that. So that's our method. So it comes into play in a big way, and you'll get a flavor for what I mean by your experimental setup being quite specific to the type of particle and the type of energy regime that you're working in. So keep in mind, this is going to be neutrinos now going forward. Um, and it's going to be the energy regime of ultra high energy neutrinos for my experiment, but we will also talk about high energy neutrinos in a bit here. Okay. And then I wanted to say that high energy is pretty broad. What I generally mean by high energy is something like 10 to the 11 to 10 to the 15 EV or so. And what I mean by ultra high energy is something like 10 to the 18 EV and above. Okay. And EV is electron volts. And you can look up what that unit means as well. Maybe somebody can put that in the chat. You were in Super K? Hello. So, Super K is a lower energy cousin experiment of what we're about to talk about here. So, welcome, welcome. Hi, Colin. Hi, Rengo. Hi, She Loved Me. What if you charged a neutrino? So, do you mean if a neutrino interacts with a photon? That's funny. Somebody said that this is going to be very theoretical. Well, I have to give you the background, which can sound theoretical, but we're actually about to talk about an experiment in particle astrophysics. So that is funny that you say that. Um, and I don't know if I should take it as a compliment that this seems very theoretical because I'm not a theoretical physicist at all, but those are very smart people. So thank you. As an experimentalist, we have to understand the theories and the backgrounds well enough and also build an experiment and make measurements and analyze, and there's really a lot more to it than just the theories. So if I know theory enough to be to come off as a theorist, then I guess that's a compliment. um so somebody asked about the gravitation. Yeah, so tides are because of the moon's gravitation. So it's really tidal force, um, which is sort of. Thank you, Leon. Um, that's an interesting point. You should ask the question about whether there's more neutrinos than other leptons. So cosmic web asked it in the context of cosmology. So we can talk about during the evolution of the universe, what kind of dominated when. So, uh, so leptons like electrons, positrons, um, interacted a lot with photons. At some point in the very early, close to the Big Bang, neutrinos actually had a bit of a breakup from that cosmic soup, blah blah blah. And we talk about how neutrinos are, one of the ingredients of the energy density of this universe. But as far as exactly how, remind me when we talk about cosmology, because I do want to give you a more precise answer to that. But speaking of some other leptons, there are some other leptons. So there's electrons, muons, taus, and then the flavors of neutrinos: electron, neutrino, muon, neutrino, and tau neutrino. So now there are other leptons like muons and taus, which are heavier than the electron, and they also have a charge, but they decay. So they are not as stable as the electron. So a muon, again, just please check my what I'm saying here, but the muon decay time is like uh what was it, like 2.2 microseconds or something like that. So it will decay after some time, so they're not considered as stable as the electron. Neutrinos are very stable, so like neutrinos are a fundamental particle, and they're not um they don't really I would say in that sense. The only thing I would think to check is whether is to give you the right numbers for electrons and positrons versus the neutrinos in terms of the percentage in our universe. And it's also interesting that there's a supernova, there's a type of supernova we've talked about. I think it's the core collapse one, where it loses a bunch of energy. I think we read that it was more energy being lost in the form of neutrinos because they can get out fast, they can get out easier from the star, um, than than in photons. So although neutrinos is not something you can see, because once again, neutrino would be something that observation through some interaction is what would be needed. Even though neutrinos is not something that you can see, um, there's a lot being produced by all these nuclear reactors, which are all the stars. And in a supernova, there are certain cases, I think there's like a lot of cases actually, where there's more energy being emitted by the neutrinos flowing out than the photons, even though it's such a bright event in the sky in terms of photons. So you have to think about the flux of neutrinos versus flux of photons and whatnot. So we are in that zone of, so when we say bright, you have to ask bright in what? Bright in photons, what kind of photons, or bright in neutrinos. So neutrinos are a common particle um, in astrophysics as well. Okay. What is a supernova? A supernova is the death of a star. So when a star dies, basically when a star runs out of nuclear power, it will have a gravitational collapse, and it will kind of collapse under its own weight, and it's not doing enough burning to make heavier elements anymore, and it's kind of dying. In that death, we basically get a cataclysmic event or an explosion, and lots of things happen in that, like there's particles getting accelerated, the different phases happening during the supernova and whatnot. So that's what a supernova is. And during that phase, during that process, um, we think what's been modeled and also worked on is that neutrinos, uh, because of their lack of interaction, a ton of neutrinos can leave the star and get emitted. And so you might, if we could have neutrino eyes, we would see that more than the photons or the light coming out. Hmm. Hello, Isaac. They're distinct from the other family of particles, quarks, primarily because leptons do not interact via the strong nuclear force. That's right. So there's the four fundamental forces: strong nuclear force, weak nuclear force, electromagnetic force, and gravitation. So we talked about how neutrinos only interact through the weak nuclear force, whereas quarks can interact through the strong nuclear force, and electrons, which is a type of lepton, can interact also, for example, through the electromagnetic force. Quarks also have a charge, so they also can interact through that. So basically, if something has a charge, that means that they can interact through the electromagnetic force. If something does not have a charge, like the neutrino, then they're not going to interact through that force, which also means that they don't really interact with light, because light is the electromagnetic wave. So it's a very, so actually, fun fact, when we first were confused by, like a long time ago, when we were confused by dark matter, neutrinos were actually considered a candidate for a form of dark matter, because think about it, dark matter interacts gravitationally but does not interact with light. Neutrinos interact gravitationally but does not interact with light. Now neutrinos interact through the weak nuclear force, and they are discovered and they are part of the standard model of particle physics, whereas dark matter is still a question mark. But you can understand why both are elusive, and so neutrinos were hmm. Each generation. Oh, yes, the leptons. I'm glad you're talking about the leptons. Each generation consists of one charged lepton and its corresponding neutral partner, the neutrino. Yes. Thank you, One Mighty. Hi, Mosin. Oh, thank you, Daniel. Thank you, everybody. Can we get 100 likes? Okay, let me keep going. So, I've been hi Daniel, hi Cosmic. I've been talking a lot, but let me cover what's on my thesis. So, first we'll look at optical Cherenkov neutrino detectors. So we are in the business of detecting neutrinos that are potentially coming from astrophysical sources. So we need a way to detect these neutrinos, right? So one of the ways is optical Cherenkov method. Now, Cherenkov is in the title of this live, and it is spelled Cherenkov. It's a phenomenon. We will learn about it here. Cherenkov radiation, pretty well known phenomenon, actually. And we will take a look. And Cherenkov in optical is thank you, Eric Sachs. Thank you. Eric Sachs has sent a floating heart. Thank you for the gifts and super chats and everything like that. I really appreciate it. That helps me with my uh, channel. Let's look at the top fans right now. I think Steven's guy reading is, yes, Steven is number one, and Reese is number two, and number three is KJ. I think Eric Sachs will rank in there somewhere soon. Thank you, Eric. So, let me talk about the oh, thank you, Macario 89. Thank you, Mac. I'll just say Mac. Thank you, Mac, for the floating heart. Thank you. Okay, so optical Cherenkov, um, optical Cherenkov neutrino detectors. Let me go like this. Okay, these look for high energy neutrinos in the energy regime of 10 to the 11 to 10 to the 15 eV. So electron volts, that's the energy unit we're using here. You can actually see how that relates to joules, for example, which is a more standard unit for energy. But in this business, we use EV a lot. Okay, so 10 to the 11 to 10 to the 15 EV or so. That is the high energy regime. In this section of my thesis that we're covering, we briefly introduced two optical Cherenkov experiments, IceCube and Antares. So these are the two names to keep in mind. IceCube is one, Antares is the other one. And these are both um, neutrino experiments, and one of them is in Antarctica. It's nice to have experiments in sort of complementary places or even hemispheres sometimes so that we have better coverage of the sky, of course. But IceCube is in the South Pole, so we'll look at that. It's being located in complementary hemispheres of the Earth. These two experiments have complementary fields of view. So this is astronomy. We care about field of view. We want to cover more of the sky. And remember, the sky we see from the northern hemisphere is different than the one from the southern hemisphere. So, also, by the way, where these experiments are on the energy scale also matters, and you want to be as fully covered as possible with multiple experiments. So, where they are on the energy scale as compared to other particle physics experiments is shown in this figure 1.5. I'll show you the, oh, actually, I did show you this figure last time, but I'll show you again tonight. IceCube is the optical Cherenkov detector in the southern hemisphere because, of course, it's in Antarctica. The observatory is located in the South Pole. The completed IceCube observatory is composed of 5,160 or 160, 5,160 digital optical modules or DOMs. each containing a 10-inch photomultiplier tube with 60 DOMs placed at depths between 1450 and 2415 meters on each of 86 vertical strings. So now this information can be a little outdated because I wrote this a few years, several years ago at this point, but I think it should be pretty close. Um, the total instrumented volume of ice cube is 1 kilometer cubed. So ice cube is literally a cubic kilometer of ice, and so hence ice cube. Antarctica is one big ice cube. Yes. And then we find a cubic kilometer of ice from there to make the ice cube. So now we'll talk about Antares. Antares is the optical Cherenkov detector in the northern hemisphere. So we mentioned ice cube, and ice cube is, of course, in the southern hemisphere. So it looks at, hi, Rocky, thank you. It looks at the sky there. Actually, we will talk about the details. It's not necessarily just that sky because there's also neutrinos that can cover, that can go through the Earth. So bear with me there. There's a few more details than is currently, what do you call, obvious. But ice cube opens up to the southern sky. So then in complement, uh, did you subscribe, guys? In complement to ice cube, we have what we call Antares. Now, Antares is an acronym, and I forget sort of what it stands for. You can actually Google it. Let me put it in the chat so you can Google it. We will talk about Antares. These are international scientific collaborations. Very good question. These are absolutely very, very international. Like my experiment, which is Anita, was a smaller collaboration, and that still included more than 15 to 20 different institutions across the world. So IceCube is huge. It's $1 billion experiment. So um, lots of different nations and their scientists are involved. Okay. So very international. It is quite common to travel a lot for these types of experiments and have your sort of like, annual group meeting in different countries in different years and stuff like that. I have a I have a friend who's on Ice Cube right now, and he's commonly, in Japan and other countries for collaborative meetings. Okay, so okay, so Antares is the optical Cherenkov detector in the northern hemisphere. It is located in the Mediterranean Sea. So the Mediterranean Sea is in the northern hemisphere. Now, Antares is a smaller experiment than IceCube. So don't expect IceCube type of numbers for Antares, but it is a complementary experiment because it's in the northern hemisphere, hence exposed to a different sky. So located at a depth of about 2.4 kilometers in the sea, okay, it consists of 12 vertical strings. So 12 is not a lot, but that's what they could do in the sea, separate from each other by a typical distance of 70 meters. Each string is anchored to the seabed, because it's quite a lot of work to put these types of instruments in, and why are we in the ice and the sea? You'll see soon here, because we want a dielectric medium for the neutrino to interact in, so that we can then measure the signature of that interaction. Okay, so we're basically setting up a system for neutrino interaction. Well, neutrinos can interact all the time, but if we're not there with our detector, then we won't know that it happened. So that's what all this setup is. So each string is anchored to the seabed and held upright by a Bowie, Bowie, I think it's the word Bowie, Bowie at the top. Um, I always have to think before I know how to say that word. Ahem. Are you sure you should not be in Bollywood and not academia? Thank you. Maybe I should be in a science movie when it gets made. Thank you, unspoken. Oh, so I put that in the chat. Where did it go? Um, did I do it? Oh, yes, I did it. Okay. So you know what Bowie is. Um, okay, okay, good on my paper. So over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes. So both of these experiments, we talked about Ice Cube and now we're talking about Antares. Both of them you will see will have PMTs or the photomultiplier tubes because we're actually going to be looking for optical signatures and you'll see where that comes from, but bear with me. So over a length of 350 meters, it is equipped with 25 triplets of photomultiplier tubes or PMTs, something that I think a lot of people are probably familiar with, building a three-dimensional array of 885 PMTs in total. So this has 885 PMTs. Um, Ice Cube had over 5,000 of those DOMs or digital optical modules, which with each containing a 10-inch PMT. So you can see how, um, Ice Cube is bigger and has more instrumented volume. In general, Ice Cube is, a kilometer cubed as indicated by its name. So instrumented volume of Ice Cube is 1 cubic kilometer. The instrumented volume of Antares, when you consider, because the Mediterranean Sea is big, what instrumented volume of it are we covering here? With Antares, it's going to be a 0.02 kilometer cubed. So it's smaller. So let me put that in the chat as well. So the total so keep this in mind about these instrumented volumes, okay? It's not easy to set up to put these experiments in business. Um, and the instrumented volume that you get is also different. But you do your best, and it also depends on your funding as well, what you can build, okay? Hmm. Um, let me put that in the chat since you're asking. This is coming directly from my thesis, guys. Whoops. Whoops a daisies. Um, that's that, maybe that. Thank you for liking the live, by the way. You guys are interesting. Oops. Okay, there. Like that. You can read. Okay, so wanted to put a little bit of information in there. Now, Ice Cube and Antares are both optimized for the detection of muons from charged current interactions of high energy astrophysical neutrinos. So neutrino would be the, primary particle, but then once the neutrino interacts in the dielectric medium, it makes what we call a secondary particle, which in this case would be the muon. And in particle physics and Feynman diagrams, if you're familiar with that, we have these different types of interactions. Okay, so what ice cube and Antares are set up for, because you could have other types of neutrino interactions, say making like a tau, and then doing going from there, but ice cube and Antares are optimized for this muon way. So neutrino going into the dielectric, making a muon, is what they're looking for. Okay, so once again, we're optimized here for the detection of muons from charged current interactions of high energy astrophysical neutrinos. Um, do I have? Do I? We can also. Did I not include the Feynman diagram for that? That's a shame if I did not. We'll keep going for a second here. Ice Cube, okay. Ice Cube uses the Antarctic ice as a target medium for high energy neutrinos to interact in. So, I mean, that's obvious, right? The dielectric medium in which the neutrino would be interacting to make its secondary particle would be the ice. And Antares uses the seawater. You can also use other dielectric medium options, by the way. Like you can use salt, you can use water, you can use ice. We have thought about doing things in Greenland. There is actually a neutrino observatory in Greenland, which I think is active right now. It's called the GNO, Greenland Neutrino Observatory. So, we did think about going to just Greenland because obviously it's much closer. Um, in the northern hemisphere, but due to a bunch of logistics reasons and things like some other reasons too, actually for Anita, um, we ended up in Antarctica. Okay, it actually ended up being the better choice. So but yeah, anyway, both of those experiments, I've mentioned one ice cube that's in Antarctica and one Antares that's in the Mediterranean Sea. They look for optical Cherenkov signatures of high energy neutrino interactions. So high energy neutrinos will come in to that dielectric medium and do something. We'll talk about that something in a bit here. It'll involve making a secondary particle, and there will be a type of radiation happening because of that, which is the Cherenkov radiation. It happens to be, in this case, optical, and we want to catch that signature with our PMTs, in this case of Ice Cube and Antares. So Ice Cube or Antares is sensitive to neutrinos of energy around 10 GeV to 100 TeV. Ice Cube was built to detect neutrinos of around 100 GeV and higher, and Ice Cube actually has a number of um, neutrino discoveries. I think Antares has some too. Not I think they definitely do. I don't want to undersell Antares. Um, but also, Ice Cube can also detect neutrinos of energy of order MeV, which is pretty low. So now, did I skip something? Where do I think I did not talk about Cherenkov radiation, and I want to. We'll keep going for a second here. We'll talk about so Cherenkov radiation is a type of radiation that happens when, due to some particle interaction, you end up with a particle shower in a dielectric medium. And if that particle shower is then traveling in the medium at a speed greater than the speed of light in that medium, so not the same as the speed of light in vacuum, but in that medium, then you get something called Cherenkov radiation. And Cherenkov radiation can be in different wavelengths. It's light after all, so it can be optical, it can be radio, whatever. So we just looked at two experiment examples that use optical Cherenkov radiation as their signature for neutrino detection. So they're letting the neutrino, I mean, we whether we like it or not, neutrinos, if they exist and if they um, are emitted by some sources and they come to Earth and they're, interact in the Mediterranean Sea and the Antarctic ice, will make these signatures of which happens to be the Cherenkov. Now, if we're ready with our instruments and we have instrumented volume in the ice or the water, then we might just be able to pick up on these interactions and thereby discover and measure neutrinos from interesting sources. So, also, I should mention all of the trouble we're taking with these types of neutrinos is also these are not just regular neutrinos coming from boring sources. These are potentially extragalactic, high energy, and ultra high energy neutrinos that we'll talk about that are coming from very interesting sources, potentially particle accelerators in the sky far, far away in other galaxies, that are, natural particle accelerators, not like the Large Hadron Collider, which is a human particle accelerator, human-made particle accelerator. And of course, that too is very interesting, and it does a number of very amazing experiments to look for phenomena that we're trying to like confirm or find or whatever. But the nature has its own particle accelerators. There are certain sites and certain processes that can accelerate particles to large energies, and those can also make neutrinos, and we're potentially looking for those neutrinos. And Ice Cube and Antares, some of these experiments actually have found such neutrinos. So these are um, astrophysical messengers that we're measuring, that are quite difficult to measure, and they're rare things, if you will. Like, these are not just um, neutrinos from the sun or something like that. Although, I mean, there are people who study that, and there is a lot of merit to that as well. But basically, this is like, no kidding, astronomy being done with neutrinos, which is a very different particle than light, and opening up a whole nother window to the universe. Okay. Thank you, Fidel Torres. Mm. Thank you, One Mighty. She's very sophisticated and classy. Thank you. She looks young and old. Oh, thank you. Thank you for following. Extragalactic meaning from other galaxies. So not the Milky Way galaxy. Uh, so that's what extragalactic is, okay? This class costs a lot of money. It's true. My advisor actually my advisor actually taught a grad level. The stuff that I'm teaching you right now is actually a graduate level. Well, I mean, it's my thesis, so technically it's not really taught in classes, but the background for this material is taught in a grad level class. So, graduate school, like where people go to get their PhDs. So, my advisor taught this class for a long time. I think she still teaches it probably. It's called astroparticle physics at the Ohio State University if you want to take it. Okay, so she's probably still teaching it. She's tenured, so I'm sure the Ohio State University is where I did this work. So OSU, in Columbus, Ohio. So radio Cherenkov neutrino. No, so now we'll come to the radio Cherenkov experiments. So we just covered once again two examples of optical Cherenkov radiation experiments, and now we will cover radio Cherenkov. So now Cherenkov radiation is just light. So as we know, light can have various, excuse me, light can have various wavelengths. And so, if you end up with some Cherenkov radiation that's in the radio wavelength, then you would call it radio Cherenkov. So, it's not anything too fancy, but same stuff, but in radio. Now, of course, however, where it's going to be very different is because of being radio, the detection method or the instrument has to be different. So we were able to pick up on the optical Cherenkov radiation with ice cube and Antares with PMTs. Those are photomultiplier tubes. Those are those can measure visible light or optical light. But now we're going to talk about radio Cherenkov, and for that we would need radio telescopes. Okay. So we would need some kind of device, some kind of measuring thing that radio waves. Okay, so keep that in mind. So radio Cherenkov neutrino experiments look for ultra high energy neutrinos. So now we're in the energy regime of ultra high energy. So this is going to be more than 10 to the 16 EV and above. Typically 10 to the 18 EV, is around where we are. The main challenge for detection by these experiments and a potential solution for detection are presented here. We also introduce two complementary, so once again, we give two examples of complementary experiments. And these are going to be Anita, the experiment I worked on, and then Ara. So kind of like girl names, but Anita is one, and then Ara is a Scarian radio array. So these are acronyms. We often go with these, female sounding names, apparently in this field, but whatever. Um, Once again, they are somewhere in that energy regime. This is going to be higher end of the energy regime, and we looked at that last time. So please do check out my live from last time because I think there was a lot of useful information there that would be good background here. Okay. Thank you, Nicole. Somebody just asked an interesting question that I have to think about. I'll come back to it. Okay. So, in this era of rapid growth, in multi-messenger astronomy, ultra high energy neutrinos remain undiscovered. So, as far as I know, because this is some years old, ultra high energy neutrinos are actually not discovered yet. Gosh. Okay. Sorry. Got distracted by an email. Um, Somebody reached out for me to advertise a lip balm, guys. So a lip balm is going to come up at some point. So in this era of a rapid growth in multi-messenger astronomy, ultra high energy neutrinos remain undiscovered. So as far as I know, I mean, IceCube has discovered a number of high energy neutrinos, but I don't think any ultra high energy neutrinos have been discovered yet. Or if they have, I didn't hear about it yet. One of those is true. One of the major challenges is that observation of these rare particles requires a huge detection volume. So remember about the detection volume and the instrumented volume that we were talking about. And this is going to be particularly important with these ultra high energy neutrinos. The I talked about how these are rare things that we are detecting, rare interactions. Well, that whole rare business is even worse in the case of the ultra high energy neutrinos. These are neutrinos potentially of the highest energies possible that we could, see in this universe from the events, the most extreme events and astronomical sites that could possibly maybe make these neutrinos. And so what we're looking for is very rare and the highest of energies of these particles. And so very, very, very rare. And we need to be able to instrument a very large volume of whatever the detection medium is in order to have any chance really of detecting these things. So now imagine, now I think you can appreciate why we go to Antarctica, which has a lot of ice, and now we'll have to come up with a way to detect or to instrument as much ice as possible. So you'll see how now we can't really do uh, quite what IceCube does with its cubic kilometer of ice. The cubic kilometer of ice might will not be enough actually, and also the how the geometry of things work, it would actually not work either. So we do have to change some things and think about how to do this a bit differently than how IceCube and Antares does, and we'll take a look. So the interaction length of an EeV or exaelectron volt, which is a 10 to the 18 eV neutrino. And a nucleus is about three. So by the way, this interaction um, at the particle physics level that we're looking at here, the neutrino coming into the ice, really the neutrino is going to interact at that level. It's going to be an interaction between the neutrino and a quark in the ice, because the ice is made of just matter, protons, and neutrons, and um, the water molecules will have nuclei, and the nuclei will have protons and neutrons, and really it's the quark that is inside that which is going to interact with this neutrino. Okay, so pretty much we will end up sometimes we say neutrino and a nucleus, or neutrino and a quark, at that point. So the interaction length, so like how far will it go before it interacts with a nucleus, and that's going to be about 300 kilometers. Okay, so less than zero point zero 0.01, so 0.01 ultra high energy neutrinos are predicted to hit the earth per cubic kilometer per year. So per cubic kilometer per year. So it's sounding pretty rare, right? But just keep in mind, uh, cubic kilometer is not that big in the world we're about to enter. Okay, so So yeah, we 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 basically have to swallow this pill that this is a very rare thing that we are trying to detect, and then we have to like really scale all our numbers and get ready for uh, bigger numbers so that we can try to catch something really rare. Okay, so just get ready for that. And welcome to ultra high energy neutrino astronomy. so, anyways, so this implies that to be sensitive to the ultra high energy neutrino flux, we need a detection volume much greater than 100 cubic kilometers. Okay, all right. Such a huge detection volume would be too expensive to instrument using optical Cherenkov detectors, as optical light is attenuated over order of tens of meters. So optical light, by the way, um, the it goes through attenuation. Okay, so over tens of meters. So that's what actually why the PMTs, they need to be kind of densely packed in an instrumented volume, which is utilizing the optical Cherenkov light. Okay, because if you're too far apart, well, the that signature light is gonna uh, get attenuated, and so you're not gonna be very sensitive to it. Okay, so now, keeping that in mind, we will now talk about the Ascarian effect, which is nothing scary. It's just going to be this Radio Cherenkov business with a few more details. Okay, are you guys ready? Or should we do this tomorrow? Are you having fun? Hmm. So somebody had asked, by the way, nice question, G. Rogers. Since ultra-high energy cosmic rays are deflected by magnetic fields, can neutrinos be used to trace them back to their origin? Exactly. One of the reasons why neutrinos are a reliable messenger is that once you see one, you can actually trace it back to the source reliably, knowing that it did not interact with any magnetic fields along the way. Okay. Somebody asked, do you vape? I certainly do not. Thank you. Thank you, Mark1756, who said nice hair. Thanks. Thank you, Nicole. Thank you, Mr. Ayub. Thank you, Fidel Torres. Some of these questions are pretty good. You should eat. She's so smart and a little smug. Thank you. I'm a little smug. Mm. Hello, City. Thank you, Moses. You look so young, but based on your intelligence, I'm going to bet that you look younger than you really are. Thank you. That's correct. Uh, thank you, Nicole. Please do enjoy. So wait, where is that question? What's the pretty South Asian women talking about? Hello, NC. Please keep going. Okay, perfect. We'll talk about the Ascarian radiation then. We can talk about dark matter. We've spent many episodes talking about dark matter. Right now, I'm not, but we will, I'm sure, go back to dark matter soon here. So keep subscribing and coming back to the lives so we can discuss dark matter together. Where was that? There is something stunning about a very intelligent woman that's also trying. Thank you, Oma King. Can you guys help me with my super chat goal, by the way? It's currently showing 0 out of 10. Where? You have nice teeth. I'd be smug too. I think I'm smug because I'm a physicist. That kind of just comes with the territory. Oh, dark matter. I saw that. We will certainly talk about. What's your favorite sandwich? I like a grilled cheese sandwich a lot. Cheddar cheese, Swiss cheese. I like grilled cheese sandwiches. So even if ultra high energy neutrinos are not discovered, we still discover something actually. So hold on and keep listening to the story here. Okay, so the lack of discovery, first of all, is still science, and it still helps us out because we can constrain the theories that predict a certain amount or a certain flux of neutrinos, etc., etc. We can also learn something about the sources that should be or should not be producing those neutrinos. And also turns out that in this experiment that we're going to focus on, Anita, in some time, probably not this live because I'm still actually in the introduction of my thesis. Believe it or not, what we've covered so far is still just part of chapter 1 of my thesis, and my thesis has, I forget how many chapters because this was a while ago that I wrote it, but this is just the beginning. Okay, so hold on, sit tight. We will make discoveries. um we will we will make discoveries in the thesis later on. And actually, don't want to make this like a suspense novel, so I'll just say that in these experiments, well, Ice Cube definitely, has a number of discoveries of these higher energy neutrinos, which are still very special neutrinos. So Ice Cube and Taurus, they have um, multiple discoveries of high energy astrophysical neutrinos. So once again, this is astrophysical, meaning not boring neutrinos from our nearby uh, neighborhood. in this galaxy, but astrophysical neutrinos, like special stuff. So these rare special neutrinos, Ice Cube and Antares have a number, especially Ice Cube has a list of these neutrinos that they have discovered. So certainly this field has a lot of discoveries to be proud of. And also remember that the National Science Foundation and other funding sources only give so much money to this field of particle astrophysics, which obviously um, has, uh, it is a very niche field, a small field. Everyone knows everyone in the field. Everybody is everybody's cousin academically in this field. Like if you did your PhD in one, you do your postdoc in a cousin experiment, things like that. I was actually supposed to be an ISQ postdoc myself, but I declined because I got a job in defense actually. But that is besides the point. But yeah, so we can only do so much. The other thing is that we still do a lot. So so um so we do have discoveries of high energy neutrinos. Now, as far as the ultra high energy stuff goes, the Anita experiment has actually a number of discoveries of ultra high energy. Um, Somebody's getting banned. Okay, ultra high energy cosmic rays. So I personally actually measured some of my own, like never seen before cosmic rays. So even though my experiment is a neutrino experiment, we ended up seeing some cosmic rays. Now that is a detail that we will get into later on, but those are pretty cool as well because these are ultra high energy. Lover Twin Pops! Hello, my friend. I haven't seen you in forever. We're talking about particle astrophysics. How are you doing, love? Is your channel 1 million subscribers now? Please do like, share, subscribe. Please do like, share, subscribe. Oh, thank you, Nicole. Lover Toy Pups is a dog channel, and she has 53,000 subscribers now. Thank you, Nicole. I have a lot of friends in different time zones. I haven't seen your lives recently. I've been on. I sometimes join your lives. How are you? Are you making money on YouTube? I have to ask my fellow channel people. But okay. So, yeah, we're talking some really niche things here. We're talking particle astrophysics. Please do like and oh, Nicole, you know what? I'll make you a mod. If you're new to the channel, please like and share and subscribe. Thank you, Nicole. Aww. Let me make Nicole a moderator. Because why not? Particle astrophysics. Oh. They're blue. Yeah, they're a little turquoise, I guess. I'm not sure. I was making lots of money, but I recently got demonetized. Because of some technical issues. I'm trying to get that figured out. What are you saying? I hope I don't get demonetized. Thank you, universe. I'm open to all the super chats, super thanks, gifts, likes, shares, subscribes. Thank you, Nicole. Thank you, love. Oh, name a car for an edit. My favorite car company is the Mercedes. E350. I'm not as smart as you, honey, but we do. Oh, no. Thank you.